Welcome to the Deep Dive. If you're joining us today, you're probably the kind of person who loves grabbing a massive stack of source material and, really extracting the core arguments, the philosophical frameworks, and those sudden perspective shifts.
Oh, absolutely.
Yeah, so if that's you, you are in the exact right place. Today, we're analyzing a really fascinating text by authors Norman Geisler and Frank Turek. And our objective is to basically unpack their highly specific synthesis of astrophysics and theology.
Exactly. The authors are taking some of the most significant scientific discoveries of the last century, particularly the ones surrounding the origins of the universe, and they're using them to build a modern case for the cosmological argument.
Right.
Essentially, they're arguing that the physical evidence of the Big Bang directly points to a first cause, which they identify as God.
It's a dense read, very deeply philosophical. But before we get into the mechanics of their actual argument, we need to establish the ground rules for you, the listener, regarding how we're approaching this.
Yes, a strict impartiality disclaimer is absolutely essential here. Because this source material navigates territory that is deeply philosophical, religious, and, well, specifically argues for intelligent design, we're going to strictly maintain an impartial stance. We are not taking sides, we aren't endorsing the viewpoints of the authors, nor are we endorsing the atheistic counterpoints that they critique in the text. Our mission is exclusively to convey and analyze the ideas contained in this original source material. We just want to explore exactly how the authors construct their argument from the data.
Perfectly said. We are here to examine the architecture of the argument itself. And to start, we're looking at a historical anecdote from the text involving Albert Einstein.
Right, which is quite the story.
It is, because we often view Einstein as this infallible genius of the modern era, right?
Right.
But the authors highlight a moment where he made a really fundamental mathematical error. And supposedly it was because he was philosophically resistant to his own discovery.
It's one of the more striking historical examples of how scientific discovery and personal philosophy can just violently clash.
Okay, let's unpack this. We have to rewind to 1916. Einstein is formulating his theory of general relativity. But as he works through the equations, he realizes they imply something he finds deeply, deeply troubling.
The universe is not static.
Exactly. It's not static and it's not eternal. The math suggests it is in motion, meaning it had a definite beginning. All time, all matter, all space originated at a specific point. And the text points out that Einstein deeply preferred the prevailing scientific model of his day, which was a static, eternal universe that required no absolute beginning and consequently no outside cause.
The authors note that Einstein actually described this implication of his own theory as irritating.
Irritating.
Yeah, irritating. So, to avoid the conclusion of a finite universe, he introduced what he called a cosmological constant into his equations.
Right.
It was essentially a mathematical weight he added to the formula to force the universe to appear static. Later, this became known as his fudge factor. It was a completely deliberate workaround to avoid the concept of an absolute beginning.
But the workaround didn't hold up, because in 1922, Russian mathematician Alexander Friedmann reviewed Einstein's equations and proved that to make that cosmological constant work, Einstein had essentially divided by zero.
A mistake a middle schooler would catch.
Exactly. A fundamental mathematical flaw driven by this intense desire to maintain the eternal universe model.
And observational astronomy soon confirmed the math anyway. In 1919, you had Arthur Eddington's solar eclipse experiment, which confirmed the bending of starlight predicted by general relativity. Then, critically, in 1927, Edwin Hubble is observing the skies through the massive telescope at the Mount Wilson Observatory. And he noticed a red shift in the light emitted by observable galaxies.
Right, and just to bridge that concept for anyone who hasn't looked at astrophysics in a minute, it's essentially the Doppler effect applied to light. Just as an ambulance siren drops in pitch as it speeds away from you because the sound waves are stretching out, light waves from receding objects stretch toward the red end of the spectrum. The more distant the galaxy, the more pronounced the red shift. Hubble was seeing this in every single direction.
Precisely. The red shift was physical proof that galaxies were hurtling away from us, the universe was expanding. And if you have an expanding universe, logic dictates that it must have been expanding from a central initial starting point.
Right.
So in 1929, Einstein traveled to California to look through Hubble's telescope himself. Confronted with the observable evidence, he dropped the cosmological constant. He later referred to it as the greatest blunder of his life.
And if we look at why the authors spend so much time on this historical pivot, It's because Einstein's reluctant admission sets the stage for their central logical framework. General relativity and the subsequent proof of an expanding universe revived one of the oldest formal arguments for a theistic creator, the cosmological argument.
The authors rely heavily on this formal logical structure. The cosmological argument is broken down into three very simple steps. Premise 1. Everything that had a beginning had a cause. Premise 2. The universe had a beginning. Step 3 is the conclusion. Therefore, the universe had a cause.
Now, for any logical syllogism to hold water, the premises have to be bulletproof. So Geisler and Turek start by defending premise 1, the law of causality. They argue this isn't just a philosophical talking point, it's the fundamental engine of science itself. Francis Bacon, the architect of the scientific method, stated that true knowledge is knowledge by causes.
Science is, by definition, the search for what caused an observable effect.
To illustrate how ingrained causality is in our reasoning, the authors use a really grounded scenario. Like, if you're driving in a car, suddenly it swerves into your lane, you don't assume the car just materialized out of nothing, right?
Right, without a manufacturer or an engine.
Exactly. Even if the driver claims the car, quote-unquote, came out of nowhere, we understand that it is a figure of speech, not an actual breakdown of physical laws. The authors argue that to deny the law of causality when it comes to the universe is to abandon the foundational principle of rational inquiry entirely.
Which brings the entire argument to the second premise. Did the universe actually have a beginning? Because if the universe is eternal, it never began, and therefore doesn't require a cause. The authors argue that prior to the 1920s, the scientific consensus allowed for an eternal material universe. But post-Einstein and post-Hubble, they argue that modern science provides overwhelming evidence for a definitive beginning.
And to organize this evidence, the authors utilize the acronym SURGE, S-U-R-G-E. It represents 5 distinct lines of scientific observation pointing to the Big Bang. The S stands for the Second Law of Thermodynamics.
Now, since we're dealing with an informed audience here, we don't need to rehash the textbook definitions of thermodynamics. We know that the second law dictates that the universe is continually moving toward a state of maximum entropy.
Usable energy is being lost over time.
Right. Nature tends toward disorder. So the authors apply entropy directly to the timeline of the cosmos. If the universe has a finite amount of usable energy, which aligns with the first law of thermodynamics, it functions essentially like a closed system winding down. If the universe had existed for an infinite amount of time, it would have exhausted all its usable energy by now.
We'd be in a state of maximum entropy.
A thermal equilibrium with no active stars, no heat transfer, and definitely no life.
They use a really helpful comparison here. Think of a flashlight left on. If you walk into a room and the flashlight is still producing a strong beam, you know with absolute certainty it hasn't been left on forever.
The batteries would be dead.
Exactly. The fact that the universe still has usable energy proves it hasn't been burning for eternity. It had to have been turned on at a specific finite point in the past.
The text actually details a revealing interaction regarding this exact point. One of the authors, Norm, was having a discussion with a materialist physics professor over lunch. The professor maintained that the universe consisted only of eternal matter.
Okay.
When the author challenged him on how eternal matter survives the constant decay dictated by the second law of thermodynamics, the professor responded by saying that every law has an exception, and his belief in an eternal universe was his exception.
Which is a remarkable concession for a physicist to make.
Truly.
When the author pressed further, pointing out that a strictly material universe wouldn't even allow for non-material realities, like the laws of physics or scientific theories themselves, the professor conceded that his stance was ultimately based on faith, which the author likened to having faith in magic.
The authors use this exchange to argue that denying the second law of thermodynamics to avoid a cosmic beginning requires a leap of faith that directly contradicts observational science.
Okay, so if we accept that the universe is winding down, we also have to grapple with the trajectory of its expansion. This leads to the U in the acronym. The universe is expanding. We established Hubble's redshift earlier, but what's fascinating here is the implication of running that expansion in reverse.
Right. If you press rewind on the cosmos, the galaxies don't just get closer together. The authors emphasize that if you rewind the expansion of the universe all the way back, all matter, all space, and all time collapse into a single point, and then into mathematically and logically absolute nothingness.
That concept of absolute nothingness is a major philosophical hurdle.
It is. Aristotle famously defined nothing as what rocks dream about.
I love that definition.
It's perfect. It is the complete absence of anything. The authors insist that atheistic or purely material explanations for the origins of the universe must account for emergence from this absolute nothingness, not just a smaller, denser version of pre-existing matter.
And they highlight a 1998 debate in Atlanta that perfectly captures this friction. William Lane Craig was debating Peter Atkins, a chemist and author. Atkins had argued in his work that the universe originated from a swirling dust of mathematical points that recombined over time.
During the debate, Craig challenged this directly. He pointed out the logical inconsistency in Atkins' model. Mathematical points are abstract concepts. They aren't nothing. Furthermore, describing them as swirling implies motion in time, which assumes space and time existed before space and time were actually created.
Right. So backstage, the authors pressed Atkins on this contradiction. They asked him directly how abstract mathematical points could be considered the absolute nothingness required before the Big Bang. And Atkins' response, according to the text, was simply to say he was very tired and couldn't answer any more questions.
Which the authors playfully suggest was him succumbing to the second law of thermodynamics right there.
Exactly. But on a serious note, it highlights the immense difficulty of explaining how something comes from absolute nothing without a transcendent cause.
The physical footprint of that transition from nothing to something is the next piece of evidence. The R in SRGE represents radiation from the Big Bang. This was the cosmic background radiation discovered in 1965, and the story behind it is a prime example of serendipity in science.
I love how this was discovered. Arno Penzias and Robert Wilson were working at Bell Labs, operating this highly sensitive horn antenna. They kept picking up this persistent, low-level microwave noise. It didn't matter which direction they pointed the antenna or what time of day or night it was. The static was always there.
They were so baffled by it that they systematically tried to eliminate every possible source of interference. At one point, they discovered pigeons nesting inside the antenna.
Pigeons?
Yeah, pigeons. They assumed the interference was being caused by the pigeons and their droppings, so they physically removed the birds and scrubbed the antenna clean.
But the static remained. Because they hadn't found bird droppings, they had stumbled upon the cosmic microwave background radiation. It was the residual heat, the literal afterglow of the Big Bang fireball, stretched out into the microwave spectrum by the expansion of the universe. It won them the Nobel Prize.
And more importantly for the author's argument, this discovery effectively dismantled the steady-state theory, which was the last major scientific refuge for an eternal universe. Agnostic astronomer Robert Jastrow noted that this radiation possessed the exact pattern of wavelengths expected for the light and heat produced in a singular massive explosion.
And that initial explosion wasn't just chaotic fire either. This brings us to G Great Galaxy Seeds. By 1989, scientists sent up the Cosmic Background Explorer satellite, or COBE. They were looking for minute temperature variations within that background radiation.
Those variations are critical. If the explosion of the Big Bang was perfectly uniform, matter would have distributed evenly and galaxies would never have formed. There needed to be incredibly precise ripples or seeds of matter that possessed just enough gravitational pull to clump together without causing the universe to collapse.
And the COBE satellite found them. The authors highlight the staggering precision of these ripples. If the expansion rate of the universe had been altered by an unimaginably tiny fraction, say, 1 part in 100,000 million more, the universe would have either collapsed back in on itself or expanded too rapidly for galaxies to ever form.
The project leader, astronomer George Smoot, was so taken by the precision that he stated in the text, "If you're religious, it's like looking at God."
Stephen Hawking called it the most important discovery in the century. These temperature ripples represent the largest structures ever detected, serving as the architectural blueprints for the entire observable universe.
Which brings us right back to Einstein and the final piece of the puzzle, the E in Serge Einstein's general relativity. General relativity doesn't just predict expansion, it establishes a fundamental relationship between the fabric of reality itself. It proves that time, space, and matter are correlative. They are entirely interdependent constructs.
You cannot have space without time, and you cannot have matter without space. They're woven together. Therefore, they could not have evolved sequentially. They all had to come into existence simultaneously at the exact moment of the Big Bang.
What's fascinating here is how the authors transition from establishing this evidence to methodically dismantling the alternative theories proposed by scientists who reject a first cause.
Yeah, they really go through them one by one.
For instance, they address the cosmic rebound theory. This is the hypothesis that the universe operates like an infinite loop. It expands, gravitational forces eventually halt the expansion, it contracts back into a big crunch, and then bangs again in an endless cycle.
It's an elegant idea, but the authors raise three major physics problems to refute it. First, observational astronomy indicates that the expansion of the universe is actually accelerating, driven by dark energy, making a gravitational collapse highly improbable.
Right?
Second, there simply isn't enough mass in the observable universe to generate the gravity needed to pull everything back.
Yeah.
And third, we return to the second law of thermodynamics. Even if the universe could bounce, energy is lost in every cycle. An infinite series of bounces would have fizzled out an eternity ago.
The authors also take on Stephen Hawking's concept of imaginary time. Hawking recognized that general relativity points to a singularity in absolute beginning that breaks down the laws of physics. To avoid this mathematically, he utilized imaginary numbers.
Okay.
By swapping out the time variable in his equations for imaginary numbers, he was able to round off the singularity, creating a model of the universe that is entirely self-contained with no distinct boundary or beginning point.
But Geisler and Turek point out a critical admission from Hawking's own writings. Hawking acknowledged that this model only works in the realm of imaginary mathematics. When you convert the equations back into real time, which is the reality we actually inhabit, the singularity, the absolute beginning, reappears.
The authors argue that a mathematical construct cannot dictate physical reality if it fails in real time.
Finally, they address arguments stemming from quantum mechanics, specifically Heisenberg's uncertainty principle. Some theorists argue that because we cannot simultaneously determine the exact location and velocity of subatomic particles like electrons, causality breaks down at the quantum level.
Right, the idea being if electrons can move unpredictably without an apparent cause, perhaps the entire universe could spring into existence without a cause.
The authors counter this by arguing that critics are confusing predictability with causality. Just because human instruments cannot predict an electron's behavior doesn't mean the behavior is uncaused. They use an excellent analogy. Imagine a beekeeper trying to observe a specific bee inside a hive. To see the beekeeper has to lift the lid and stir up the hive.
Exactly. Our very attempts to observe subatomic particles involve hitting them with light or other energy, which inherently alters their behavior. We are disturbing the environment we are trying to measure.
Yeah.
The authors argue that human observational limits at the quantum level do not negate the macro-level law of causality that governs the entire universe.
Okay, let's unpack this next transition because it's vital to how the authors shift from physics back to philosophy. Having defended the physical evidence for a beginning, they introduce the Kalam Cosmological Argument to reinforce it conceptually. This relies on understanding the nature of time itself.
The text asks the reader to visualize a timeline. Imagine history stretching out horizontally. The segment we occupy right now is labeled Today. As you look to the left, you are looking back into the past. The central question of the Kalam argument is whether that line to the left extends infinitely.
If the universe is eternal, then there must be an infinite number of days before today. But the authors argue that this creates a logical paradox. You cannot traverse an infinite number of steps to reach a destination. If the number of days before today was truly infinite, today never would have arrived.
From an analytical standpoint, the text distinguishes between mathematical infinities and concrete infinities. Mathematically, you can infinitely divide the space between 2 points on a graph. But in physical reality, an infinite series of concrete events is impossible.
Right, you can conceive of an infinite number of books, but you cannot physically place an infinite number of books on a bookshelf.
Exactly. Time, in this context, is comprised of concrete events. Days actually happen. Because we have arrived at today, the sequence of past events must be finite. Time itself had a beginning.
So, what does this all mean? If S-surge proves the physical universe had a beginning, and the Kalam argument proves time itself had a beginning, we are left with the ultimate question. It is the one skeptics immediately raise. If everything needs a cause, who made God?
It is the most common counter-argument, but the authors address it by pointing back to their original premise. The law of causality does not state that everything needs a cause. The precise phrasing is that everything that comes to be needs a cause.
And that comes to be phrasing changes the entire philosophical landscape.
It does. If the universe had a beginning, it came to be, therefore it requires a cause. However, whatever caused the universe, the first cause, must by definition be uncaused. It did not come to be. It exists eternally outside the framework of time.
The authors argue that logic dictates only two options. Either the universe is eternal or something outside the universe is eternal. Since the data overwhelmingly points to a finite universe, we're left with the conclusion that an external, eternal cause exists.
And this is where the authors synthesize the physics into a profile of this first cause. They do this without referencing religious texts, relying purely on the scientific attributes required to initiate the Big Bang.
Let's run through those characteristics because the logic is fascinating. If the first cause created time, space, and matter, it cannot be bound by them. Therefore, this cause must exist outside of time, making it timeless.
Right.
It must exist outside of space, making it non-spatial, and it must be without matter, making it immaterial.
Furthermore, to bring the entire universe into existence from absolute nothingness requires an entity that is unimaginably powerful.
To design the universe with the extreme precision we see in the great galaxy seeds and the expansion rate, this cause must be supremely intelligent.
And lastly, the authors argue the cause must be personal. This requires a bit of philosophical unpacking. An impersonal mechanistic force cannot spontaneously choose to change a state of absolute nothingness into a time-space material universe.
Right. Initiating creation requires volition. It requires a choice to act. Therefore, the first cause must possess a personal will.
Timeless, non-spatial, immaterial, immensely powerful, supremely intelligent, and personal. The authors conclude that these attributes derived purely from cosmological data align perfectly with the theistic concept of God.
The text wraps up this extensive argument with a highly observant quote from Robert Jastrow, the agnostic astronomer we mentioned earlier. He wrote a book titled God and the Astronomers, which explores the profound psychological trauma the scientific community experienced when the Big Bang evidence emerged.
Trauma is a strong word, but it fits.
He observed that scientists who operate on the strict assumption that all phenomena can be explained by natural laws are deeply disturbed when the evidence points to a beginning under conditions where known physics completely break down.
Jastrow describes a kind of religion in science, a deeply held faith that every effect has a purely naturalistic cause. When the expanding universe implies a supernatural first cause, it shatters that paradigm.
Jastrow ends his book with a powerful metaphor. He writes that for the scientist who has lived by his faith in the power of reason, the story ends like a bad dream. He scales the mountains of ignorance, he's about to conquer the highest peak, and as he pulls himself over the final rock, he is greeted by a band of theologians who have been sitting there for centuries.
It is a brilliant visual. Whether you are actively studying astrophysics, preparing for a philosophical debate, or just profoundly curious about reality, this text demands a rigorous reevaluation of how we view the cosmos. It forces you to look beyond the equations and confront the absolute limits of human observation.
It really asks us to look closely at the boundary line where physics ends and philosophy begins.
This raises an important question, something for you to mull over as we conclude. We've spent this deep dive analyzing how time, space, and matter are tightly bound physical constructs that abruptly sparked into existence from absolute nothingness. If we accept that premise, what does that imply about human consciousness?
That is a massive question.
If the entire physical universe is finite and caused, is the human mind's ability to even conceptualize abstract infinities merely a biological byproduct of that initial physical Big Bang? Or does the very existence of our subjective awareness, our capacity to logically deduce our own origins and ponder timelessness, hint at something that operates fundamentally outside the boundaries of those physical laws?
Wow.
If the universe sprang from a timeless, immaterial cause, could human consciousness be a reflection of that immaterial reality?
That is exactly the kind of perspective-shifting thought we're looking for. Thank you for diving into this complex material with us. Keep questioning the boundaries of the universe, and we will catch you on the next deep dive.